Hi students, today we are going to discuss the mutual inductance of two long solenoid. The previous class we have already learned that how does the self-inductance take place. Here we consider two solenoids. And the total number of turns in the first solenoid may be taken as S1 and another solenoid S2. The size of these two solenoids are different. S1 is small and second one is larger, so that the small solenoid can be completely immersed in the second solenoid. Now, the total number of turns in the second solenoid is N2 and a current I1 is flowing through the first solenoid, and the total number of turns they are taken as N1 is equal to N1 into L, where N1 is the number of turns per unit length and L is the length of the solenoid, and N2 is equal to N2 into L, where N2 is the number of turns per unit length and L is the length of the solenoid. And also R1 is the radius of the first solenoid S1 and R2 is the radius of the second solenoid. So these are the assumptions here. And now we set up a current I1 is flowing through the solenoid first. So what will happen? A magnetic field will be set up in the axis of the magnet, and this magnetic field set up here will link with the second solenoid and a magnetic flux will be produced there. So this magnetic flux will be linked with the second one. So the magnetic field produced here, that is V1, that is equal to mu 0 into N1. The magnetic field produced by the first solenoid is V1 is equal to mu 0 into N1 into I1. Then the magnetic flux linked with the second solenoid. Then the magnetic flux linked with the second coil, that is N2 phi 2. The phi 2 is the magnetic field associated with the second coil, and N2 is the number of turns of the coil 2, S2. And that is proportional to the I1, the current flowing through the first coil, and the proportionality constant called mutual inductance of the coil 2. And this mutual inductance is also referred as the coefficient of mutual inductance. The resulting flux linkage with the coil 2 is N2 phi 2 is equal to N2 can be written as N2L. Pi R2 square is the area of the coil. The magnetic flux linked or the magnetic flux produced by the coil, that is mu 0 into N1 into I1. That is the total flux linkage to the coil 2. And now we can write this mu 0 into N1 into N2 into pi R2 square into L into I1. N2L is the total number of turns of the solenoid 2. So this equation can be written as M21 is equal to mu 0 into N1 into N2 pi R2 square L. And when we equate these two, and this I1 will be cancelled. So what will remain? N2 phi 2 is equal to N2 L into pi R mu 0 into N1 into N2 into pi R square pi R2 square L into I1, and that will be equate with M21 into I1. Then I1 and I1 will be cancelled. What will remain there? M21 is equal to mu 0 into N1 into N2 into pi R2 square into, that is the mutual inductance of the second coil when a current magnetic field is produced by the first coil. And now we reverse the case. And when we reverse the case, a current I2 is flowing to the second coil, and when it is connected with a battery. Now here a magnetic field is produced through the axis of the second coil S2, and a magnetic field will be produced there, and the magnetic field will be V2 is equal to mu 0 into N2 I2. And then this the magnetic field produced here, a magnetic flux will be there, and that magnetic flux will be linked to the first coil S1, and the magnetic flux can be written as N2 N1 phi 1, and this N1 phi 1 can be written as is proportional to the current flowing through the coil and M12, that is the mutual inductance of the first coil. And now this magnetic flux produced N1 phi 1 can be written as total number of turns of the coil, that is equal to N1 into L, and again the area of the coil, that is pi R1 square into the magnetic flux associated with magnetic field produced by the coil is mu 0 into N2 into I2. Then now when we write this, mu 0 into N1 into N2 pi R1 square into L I2. So now equate this one and this one. What will get? We will get mu 0 into N1 N2 by R1 square into L. From this equation and this equation, and we assume that M21 is equal to M12 is equal to M. That is, the mutual inductance is the common factor in between these two equations. They are equal. Here the first solenoid is effectively immersed in the second coil. The area of the first coil, this is the area of the first coil, and this area of the second coil. And if this coil is immersed in this second one, then how much area will be influenced by the magnetic flux? Suppose the magnetic flux is produced by the second coil. How much area will be affected to the first one? This much area only. And so here the area or the radius, they are not changing the area. And if this first coil is producing a magnetic field, and the magnetic flux produced by the first coil is linked with the second one, and if it is immersed, then what happened? How much area of the second coil will be influenced by this one? The magnetic field produced by the first coil, this much area, that means the area is equal to the first coil, and this much area only will be affected by the coil. So in both cases the value of area and that remain constant, and until there is no change in the radius. We have N1 into phi 1 is equal to M1. So for this current varying with the time, and this can be written as For the current varying with time, this can be written as dN1 divided by dt is equal to dm12 divided by, then the EMF E induced in the coil is then written as dN1 divided by dt. So E is equal to, the EMF induced E is equal to minus M into dI2 divided by is the induced EMF produced in the first coil.